Welcome back to my channel. Today let's go over a medium that I just solved on my own. So again, really happy about that. This is similar to a question that I just solved in the last video. So let's go over it. The strategy is similar. So essentially you're given an integer array and you want to find the absolute sum of the differences of each similar element. So for 1, you would map that to index 1 and 3, and then you would, for example, when you're visiting index 1, you would do, well, for example, index 1, you would just do 1 minus 3. Absolute value of that is 2. And then for 2, you would just do 0 minus 0, 1, 2, 3, 4 is going to be 4. 0 minus 4 is 4. So same strategy as before. We're not going to go over the n squared solution here. Let's just go from left to right. And basically you just want to do this and find the sum of the indices of the same value minus the current index as an absolute difference and add them together. If this element only appears one time in the array, it's obviously going to stay 0. And so it's pretty self-explanatory. Let's go ahead and iterate over our array from left to right. And let's create a dictionary, the purpose of which is going to be to map the current value to the index. It's going to be in order because we're going from left to right, and indexes increase from small to large. So let's print D. As you can see here, index value 2 is at index 0 and index 4. Value 1 is at index 1 and 3. And in value 3 is at index 2, 5, and 6. So cool. So now, because we're going to be running a binary search to find the absolute value, let's go ahead and create a prefix sum dictionary, which is going to take each value and accumulate it. So 2, 7, 13. And this makes it easier to run a binary search later because we want, for the current index, we basically want to split it in half. And so for example, if we have 3, 4, and we have 6 as the current index, and 8 and 9, these are all indices, we're going to get the sum, which is 7, and then we're going to get 6 times 2 because the length is 2. This is always going to be bigger than 7, so 12 minus 5. So in that regard, we don't have to do the absolute difference anymore because we already know that this is bigger than this, and the absolute difference is going to be positive. And then we know that the right side is going to be 17 of a sum minus 6 times 2 again, because we know the right side's smallest value is going to be bigger than this. So we're just going to do the current value times the length of the right side. And since this is bigger than this, again, we don't have to do absolute values, which makes this simpler. So knowing that, let's go over each value in our dictionary because each value was already mapped to its respective index appearance in the list. And let's go ahead and take that value, create a key in our new dictionary, and set it to the accumulated version of that list. So list of itertools.accumulate dk. Let's print PD so you can see and visualize this. It's much easier that way. 2, 7, 13, again, just accumulating the sums of the indices where this value appears inside of the input. So now that we have that, we're ready to iterate over A one more time. And now we can declare a variable called now because we're going to count the number, we're going to count the sums of the current index. So 0 minus the same values, indexes that are different from the current added together minus the current index. So we're going to do a binary search, bisect left inside of DA because DA is the current element, and we're going to look at all the indices where it appears. And then we're going to do a binary search on I because again, we're trying to make this list where we're trying to find exactly where the current I goes. So we can subtract this from the lesser part times the length of the lesser part, and then the greater part sum minus the current element times the length of the greater part. So we don't have to deal with all negatives and absolute values. So right is bisect right of D of A of I. And now let's go ahead and print, just to show you, left, let's just call this d of a up to left. And then right is d of a from right to the end. Let's print left, and right. Let's also print I. This is our current index that we're looking at from left to right in the array, right? So if both lists have something, then we have something to go on for that current list. So it doesn't even matter. We can just, again, this is always going to be smaller than the smallest element here because of the binary search. Same here, smaller, greater than current, right? So this is actually O of n, so we're not going to do that. Instead, what we're going to say is if the index that we get from the binary search is bigger than 0, then we know we have elements on the left side, right? Likewise, if the index of the binary search is less than length of the current list, then we know we have elements on the right side, right? This is not empty, unlike this. This is like this. So now what we can do is, again, let's call this low and high. And the low is just going to be the sum of everything up to left, right? So now this is where the prefix sum comes in handy. Let's call this pref is going to be PD of A because that maps to the accumulated list. So we have that of the current value we're looking at, 3 for example. And then now low is just going to be pref of left minus 1 because again, if you want to get all the sums up to this point, then it's just going to be 7. If you want to get all the sums up to this point, it's just going to be 13, right? 2 plus 5 is 7 plus 6 is 13. The high is going to be the current I, the current index, right? So times the length of left, which is because left starts from 0 all the way to the end. So whatever left is going to be the length of the current array that we found through the binary search. And then we can just add high minus low because that's going to give you the difference between this sum minus this times the length minus this sum, or this times the length of this minus the sum of this, right? So, and now let's do the same thing for the right side. And the low is just going to be, instead of this, the low is going to be this. So it's just going to be the current index times the length of D of A, which is the length of the list we're looking at, not the prefix one, the length of the list we're looking at, minus right, because right is the index. So right you can think of as like going this way. Left is going up to a certain point, right? And then right's just continuing from that point. So the total array's length minus whatever right is going to give you the length of the current subarray. And then high is just going to be the sum of this right subarray, which is going to be, if right is less than or equal to 0, high is just going to be the last element, because that's the sum of the whole thing. If there's no left part, right, if we're here, then the total sum is just going to be pref of -1. Otherwise, high is just going to be pref of -1 minus pref of right minus 1. So for example, again, for finding this subarray sum, it's this minus this. 13 minus 2 is 11, right? And then again, now plus equals to high minus low to get the difference. And then we can append now to our result at the end, because we want to return a list of integers and then return result at the end. So this should not get time limit exceeded. And there you go, passes all test cases. So I know it's not the most efficient solution, but I did come up with this completely on my own. So I'm really proud of that. And I think it's not very hard to understand if you know how binary search works and you get the idea of what I was talking about in terms of this. So sum of this minus this times length of this, sum of this. So this times the length of this minus the sum of this, right? So right side and then left side. So I hope this video helps, and consider subscribing if you haven't, and stay tuned for more content. Thank you for watching.